So now let's do a deep dive on the access layer. The system architecture diagram that I'm showing here, this is a very favorite interview questions for many companies, especially something that's related to, even remotely related to wireless communication. This is a guaranteed question in most of the interviews. So what happens here is they basically ask you, what is the system architecture from the bits all the way to the antenna? What is happening there? And why is this important in network planning? Because as we're going to see in an example now, all these details are really important in coming up and making a decision how far a cell tower can reach, or how far a Wi-Fi router can reach. How can we make the design better? How can we make the network plan much more optimized? And it's all connected to this. So that's the reason I wanted to emphasize on this architecture. And this is a really critical piece. I think this one slide, if we focus on it and understand it carefully, the next 4-5 slides are all dependent on them. It's a small modification to this and it'll be easier to follow. So let's focus on this system architecture here. So it starts with interface to MAC and encoding. What this means is MAC is a medium access layer. So this is a physical layer that we're talking and looking at here. What happens before this medium access? And it starts with encoding, which is error control coding, as we call it. That gives you some set of bits that need to be transmitted. And the very first step is mapping the bits to a modulation scheme. So we can take a 4-QAM or a 16-QAM or a 256. Map each of those few bits, group them, and then map it to a complex symbol. And once we do that, what happens after that is OFDMA or SCFDMA. These are modulation technologies that are used in different standards. So if it's LTE, it's OFDMA or SCFDMA. If it is Wi-Fi, it is again OFDM. And once we have this strategy, this is where the digital to analog conversion happens. And also it gets up converted to a higher frequency. It can be 2.4 gigahertz or any frequency or the band of interest. And the power that is given as input to the antenna, the signal power, is what we call as the transmit power, because I'm going to use that term again and again here. So just wanted to make it clear. So that's what I mean by transmit power. And then the antenna adds its own antenna gain to it. So the antenna boosts the transmit power in a certain direction and sends it out. And on the other side, it's easier. It's just the opposite of that. The antenna picks it up, the signal. But of course, note that the signal is going through a huge propagation loss in the wireless medium. And once it's on the receive antenna, of course, boosts the signal. And then you have some barely received signal, which we call as the RSL, receive signal level. And of course, that is being down converted to a smaller frequency and then digitized. And again, the opposite happens, OFDMA, modulation, again, mapping from, sorry, this is symbol to bit, not bit to symbol to bit mapping. And then we go to decoding and send it to the higher layers. So this is a breakdown of the physical layer. And if I have to capture this entire diagram in a couple of equations, so that's what I'm calling it as link budget calculation. So what this means here is we have to ultimately calculate the RSL, because RSL is what determines your signal quality, right? What you receive is your signal quality. So RSL is nothing but, it's a simple accounting, transmit power plus your antenna gain, because antenna gain acts in your favor to the transmit power. It boosts the transmit power. So whatever the transmit power is, add a gain to it. And propagation loss does not act in your favor. It actually degrades the signal. It could be a tree or a building that is cutting down or attenuating your signal. So that's why you have a minus there. So you subtract the loss that you're going to suffer in the medium. And then again, the receiver antenna acts in your favor, add it to the budget. And then there'll be other losses such as the equipment manufacturing or implementation losses. So we add it to the budget as well. That's your level. And of course, something else happens in the receiver, which is nothing but the noise power. So what that means is the receiver electronics, as we all know, electronics always have this noise being constantly generated in them, and that is being added to your signal, which means it degrades your signal quality. Now you just don't have only your barely attenuated signal, but it's also signal plus this noise that is being added up. And there is also another term called noise figure that is added up here, which is, again, how much of a degradation the signal is suffering because of these equipment, the hardware, electronic that is there in the receiver side. Ultimately, we get what is called as SNR, signal to noise ratio. This should be a ratio in the linear scale, and I have everything here in the TB scale, in the logarithmic scale. That's why I have RSL minus noise power. Otherwise, it would have been RSL divided by noise power, which makes sense. It is And this signal to noise ratio is the one that determines the throughput or the quality of your communication. Even if you have a very high signal that you're receiving here, like high RSL, but but you have a noisy receiver or a low quality equipment that you have in hand, then that could degrade your signal quality, because it's not the signal quality that matters, it's the ratio of the signal to the noise that matters here. And mapping that signal to noise ratio to a throughput is what is determining your finally the user's quality of usage. So I believe this is the framework that I wanted to set up here. So, and now we can move to some examples, make slight modifications to this diagram and analyze how things change, okay? So now this is for an access layer. Let's do a deep dive on access layer uplink. So what I mean by uplink here is from a cell phone to a cell tower, that's uplink. Whereas the other way, from a cell tower to a cell downlink. So when you're recording a video and then when you upload a video, let's say to any to YouTube, then what you're doing is you're sending your video back to the network, right? So you are uploading it. So that's what we mean by uplink. So when it comes to uplink, your transmit power is generally limited because your phone is the one transmitting, so it can only do 23 dBm, and there is no antenna, heavy antenna on your phone. It's a lossy antenna, so you don't get any antenna gain. So that's 0 dBi. And then you have typically a 120 dB propagation loss, because that's a huge loss going from here to here, which is typically for less than a kilometer. And then on the base station side, you have a heavy antenna that is placed there that can give you an 18 dB of advantage. And then some additional 2 dB losses for connectors and all those things that happen, the non-idealities that happen in the base station and also on the cell phone. So ultimately you get to this power level of minus 81 dBm. You can always convert this into watts or milliwatts and look at it from that perspective as well. And now you have it. It's easy to calculate signal to noise ratio. That is, what is the noise power that is typically added by these electronics versus the signal power that's received. And 11 pretty good number, which means your noise is 11 dB lower than your signal power. That's what this means. And mapping this to the throughput gives you what is your final throughput that can be achieved. How many Mbps can you get from this direction of the link, that is the uplink. Similarly, I can do the calculation for downlink. See, as you see, there's no big change to the overall framework. I just change the numbers here. I go to the RSL calculation. Now it's a base station, a cell tower that's transmitting. It is much more higher than your cell phone. So it's 30 dBm. And you have a gain of 18 dBi. And again, the same loss, because let's say it's the same distance as before, but you have zero gain on the cell phone side. And of course, again, some losses. That gives you a much better signal quality now. Earlier it was minus 81, now it's minus 74. And you can see that is reflected in your SNR here, and hence it can be a better quality. That's why sometimes downloads have much higher quality than uploads. Uploads sometimes they struggle hard. That's because of this difference in the levels that the cell phone is transmitting versus the base station is transmitting. Similarly, we can do a link budget for Wi-Fi as well. Again, Wi-Fi, you can see I have reduced the propagation loss from 120 to 110 because it's a short distance communication. There won't be a huge loss. Of course, the walls and other things are blocking you in your own house, but we can account for it. Again, it's the same methodology. You can see, given that the propagation loss is smaller now, we still get to a decent SNR. Again, we can achieve some throughputs here that are reasonable. Now, so that's about the access layer link budgeting. It's basically to identify the cell radius. That's what we have been reviewing. And now we move on to backhaul networks. So just to clear some of the synonyms here, this is often referred to as distribution networks or transport network, or some people also call it backbone or the core network. So they're all synonyms, so we can use them interchangeably in a loose sense, of course. Architecture and link budget, I'll just share some examples for fiber link, wireless links. What if it's a satellite link? I just wanted to highlight the challenges in these different link budgets. Again, we'll follow the same link budget evaluation procedure that we described earlier. Let's look at a fiber link, okay? So as you can see from the block diagram here, the encoding, modulation, the single carrier block framing, which is similar to OFDMA, but a single carrier version of it, and the upconversion, they all remain the same, but the medium is now not a wireless medium, it's a fiber medium. And the advantages of using fiber is that it's extremely low loss, and it can travel up to hundreds of kilometers. It can even go underwater, and the loss is still very minimal compared to what we see in a wireless propagation. So we have a transmit power that is fed into the fiber, and then we have an RSL that is coming out of the fiber on the other end. And similarly, we can do a quick link budget calculation here and see how long can you plan this link. So some of the advantages here are fibers are much more reliable. They're not dependent on weather conditions, whereas sometimes the wireless links, they get affected by rain and other things, or even something, if a tree grows in the path and it blocks the wireless link, that can significantly degrade it. Whereas fibers are much more reliable and they can travel much longer distances. And they generally tend to have much higher bandwidth than the wireless medium, because for the wireless medium, we have to purchase a spectrum which is expensive, and that limits us to purchasing a smaller amount of spectrum. But fiber definitely does offer this higher bandwidth opportunity. Whereas now when we switch to a wireless link, which is similar to what we have seen, except that now we have a really high gain antenna. This is not any user handheld device. These are devices that are placed on top of buildings or on top of towers, from one tower to the other tower. So there are two antennas there on both sides, because earlier, if you remember the link budget, we had a good 18 dBi gain on one side, dBi on the other side, right? Because the other side is always a user device, which cannot have a bigger antenna. Whereas in this case, both antennas are not user devices, and they are typically mounted somewhere else, maintained by a different company. So that needs to be, in that case, both of them can go as high as 36 dBi here. These are like the highest possible numbers I'm showing. And if you see the propagation loss, it has gone significantly up. Instead of using 120 or 110, now I'm using 190. So the reason for higher propagation loss here is they tend to go much longer distances than a cell tower or a Wi-Fi router. A cell tower would go for a couple of kilometers or so, whereas this can go up to tens of kilometers, maybe 60-kilometer maximum, because after that you hit the curvature of the earth, you cannot really see each other. So having such long distances gives you the heavy loss, but the antenna gains just make up for it. And then again, you end up getting the same SNR that is typically possible in any other scenarios. So the benefit here is that they deploy, whereas for fiber, you'll have to dig the ground, make the plan, get the permissions and everything. And then it takes a while to deploy fiber, whereas wireless links are easier to deploy. And they're also flexible for future modifications. You can always turn them around. You can close a link easily and then build a completely different network. So rerouting is much more easier here versus what we have in fiber. And now satellite links. So there is a very specific challenge with satellite links. So if you look at, again, the structure remains the same. But the antennas that are there on the satellite needs to be low gain because of low weight. Generally, there is one rule of thumb: the lower the antenna gain, it can be a smaller antenna. If it's a higher antenna, there is higher gain to it. So if you want to put a heavy antenna in a satellite, that's not possible because there's always a weight constraint to it. And also, if you see, there is also a transmission power constraint because the satellites have a limited power budget. They have to operate within that power. So we cannot power as it can be done on the ground, right? So there is a low transmission power and then low antenna gain. And now coming up with the overall communication system design that enables this link is generally a challenge. And there are limited devices that are available in the market that can close this link at certain distance. And on the ground side, we have something called as the UT, or the user terminal antenna, which can be bigger, of course, since it's on the ground. It can hold a heavy load and it can have higher power. But again, the uplink versus downlink difference comes into picture. Sometimes it gets hard for the uplink, whereas the downlink so it gets hard for the downlink here, not the uplink. I've put together a sample link budget here for antenna as well. The main advantage here is it can go extremely long distances, like thousands of kilometers. Instead of burying the fiber on the ground for those many distances, it's better to put a satellite that could turn out to be much more cheaper sometimes. But the system design is always challenging. And of course, it has a greater effect on the cost model in terms of deployment. And again, decommissioning is an issue because once it's deployed, there's no way to bring it back. Typically, they just leave it out there. They just deactivate it and leave it there. So now that we have covered the access and backhaul planning strategies, and I think we did do a deep dive on the link budget calculations. I look forward to questions. If something is not clear, I'm happy to address them in the Q&A. So having said that, I wanted to give a quick overview on the network planning tools, which are generally used in the industry very widely. Whatever I've described, all these concepts are being included in this tool. These tools are designed to understand these concepts, and they give you ready-made user interface that you can play with and run certain analysis. So, for example, there would be a button to click the option, and once you click it up, it'll open and it'll ask you for all the parameters, like what is the antenna gain, what is the transmit power, what is the link distance, and it'll give you the RSL. So those are like ready-made features, but it's good to learn the theory, what we went through, to understand how these tools operate. And worth mentioning, some of them are Force et al. And we have a Planet, we have Link Planner, which is much more simpler version. Force et al. Is much more sophisticated. It offers many features. It offers even automated cell planning, so you can just mark the area of coverage and let it determine where it has to place the cells, what frequencies it can assign. It does some heuristic optimization in it, and then gives you the final result. You remember the 3 cell towers that I was doing? You can just mark that area and then give it as input to the tool. It will find the best possible locations of those cell towers for you. Now, using these tools, since it's a very complicated tool, the tool itself requires some level of training, and all these companies offer training as well. When they onboard you to work for them, they offer training from ATOL or Planet, and I think that's essential. But in order to go through that training, understand the operation of the tool, it's very important to have a good grasp of the fundamentals, which we just went through. Typical advantages of using these tools are, they have most of the features automated. Optimization is all well defined, and it also has a facility to include the field measured data, which we'll discuss it in a bit. And it gives you nice reports that can evaluate the performance. And it's easier to share the design files across companies. Usually it's not just one company working on a cell network design. Multiple companies are doing multiple jobs there, so it's easier to share, get a design file out of this and share it across multiple parties. So this is what I wanted to touch upon. Another item is the need for field survey. You might see some of these vehicles around that go around and make measurements. So this is prior to a deployment. What happens is you try to set up a dummy antenna, you use a dummy frequency on the tower, and then use another antenna on the vehicle, and then you go around, drive around the area and measure your propagation loss, signal power that is being received, any interference that can occur possibly. This will help you get a realistic perspective of that field in a very detailed manner, and this data can again be fed into the network planning tools so that it does the optimization, taking these real measured data into account. So that's what a prior deployment field survey means. And then there's also a post-deployment field survey. This is generally done by bigger companies like Ericsson or anyone who have their equipment deployed in the field. They send out a team there to do a post-deployment survey to see how their equipment are functioning once they're deployed, how download any data, how SMS is working. So all those things, someone has to go and check it out. That's what a post-deployment drive test means. And in case of Wi-Fi, drive test is not necessary since it's just between a home. And generally, every home is different, and they've been studied in the past. We have a lot of papers and studies on them. There's no need to do any field survey for Wi-Fi. However, nowadays we have malls, multi-dwelling units such as apartment buildings. They need Wi-Fi installation. There needs to be some amount of careful planning that's required when there is a multiple installations there, because we have to install it in a way that is not interfering with each other. This takes into account crowd density, the business hour requirements, at what time. Let's say if it's a mall, it's active at a certain time. We need to guarantee a certain throughput during those busy hours. So so all those things go into a field survey for a Wi-Fi before a Wi-Fi installation in a building service. And finally, I'd like to touch upon a business case evaluation. So this basically, whatever we have studied so far, I just wanted to show how it connects to a business strategy, how it connects to the end finances, or as we call it, return on investment. So let's just define this here for a bit. So business model is a calculation system now that takes all the investment cost numbers as input. So this can be your tower cost if you're building a tower. It can be your equipment cost, the antenna cost, any cost that goes in as input. And also you take into account the amount that can be charged to your subscribers. So for example, if you're planning to have a network deployed in a certain area, there will be a guess on how much each subscriber would contribute. And then based on that, you can estimate, given this population density, I will have so and so subscribers here. With that, I can get so much of monthly returns on my investment. So in order to do that, a key input here is the field surveyed parameters or your network planning outputs. So based on your network planning, you will have a coverage area. And with that coverage area, you can estimate accurately how many subscribers you can possibly get. So that's why, I just wanted to show how the network planning ties into the business modeling approach here. And now with all those inputs, the investment that goes into it, the cash return that we get from the subscribers, and the network planning insights, with all those inputs, what we can do is that we do what is called as a cash flow computation. And after that, we can definitely get a projection on the return on investment, like how much we have invested versus how much we're getting, what is our profits. Generally, the profits do not show up in the first few years. It takes a few years that you are on a loss. And then after that, the curve slowly goes up, and then you are on a green side, start seeing the profits. So this will give you an insight of how many years is that non-profit area and how much of an investment that would take. It'll give you a projected area where a year after which you can start seeing the profit slowly increasing. So that's about it on the business model here. This is basically a connection between all the technical studies we have done all the way to your return on investment. I'd like to spend a few minutes here on the employment and research areas. So in order to make it a little more clear here, I've organized them as different categories of employment. Okay, but before we get into the research areas, let's just touch upon the employment areas here. So the first category here is what we call as operator equipment manufacturer, or OEMs. So what they do is that they are the companies that manufacture the equipment that go on cell towers. So the base station has their RF front end on it. We call it a remote radio unit, RRU. And then we have a BBU, a baseband unit. So all these units that build and construct a cell tower, in terms of electronics there, the communication system electronics, there are companies that are focused only on that, such as Ericsson, Nokia, Samsung. They're focused on that, and that's an important piece of their business. And these companies do have a lot of job openings that target on designing these communication systems. See, now this is not a direct network planning job, but it is a job that indirectly involves network planning. When you design some equipment for a base station, it is necessary to keep the network planning in mind, because that's going to be the end application, right? And that derives your requirements of these equipment that you would be designing. Generally, a wireless communication system architect is a widely preferred role by most engineers. They would want to come up with the architecture that solves a certain problem, that makes the network planning more easier, or makes the network more efficient, and saves a lot of money in terms of their ROI. And wireless systems engineers or systems design engineer, these are all very familiar job roles. They're all very good job roles, and they have a good career track as well within the company. Some of them branch out as a management track, because you will have to lead a bunch of engineers as a manager. And then sometimes you can always evolve as a engineering expert, which is not managing people, but more evolving on the engineering side, becoming more of a principal engineer rather than a manager. So some people choose that career track as well. Just a few examples. There are much more companies than what I've listed here. And just another category is on the network operators side. So companies like AT&T, Verizon, or even T-Mobile, they have a lot of network design engineer roles or network validation engineer roles. Earlier, we saw an equipment design level, but now at a network design level. How would you plan a network? What will be a planning strategy that can benefit the company? How we can rapidly automate this process? How we can hire more people to start the planning process? How can we outsource this work? So they think of those type of aspects from a network operator perspective. So now they're not into any design of equipment, but from a network planning perspective, they need more support there, an engineering support. Field validation engineer commonly is also a common need for network operators. They would like to send engineers to the field and verify if their deployed network is acting up to the standards as promised. And this eventually, if they do not act, then these engineers are the ones that drive the roadmap for the upcoming network designs. And finally, we have another category here, which is the network planning services. Now, these companies that do network planning services are generally hired by either the OEMs or the network operators. They hire these companies because sometimes these OEMs or network operators, they might not have resources to conduct network planning. They might be busy with something else, such as the network design or at a validation stage. They would want to outsource this. This is a job that can easily be outsourced to a different company. So that's why we have, nowadays there are so many new startup companies coming in this area that focus on network planning services. So basically, they have to gather the requirements from either network operator or an OEM, and then they go to the field, they conduct the survey, collect the data, and give it back to them. But then they are still a company on their own, and they hire engineers like drive test engineers, OTA test engineers, a very famous job description that you can find. Just search for OTA engineers, over the air test engineers. And FAE, field application engineers, another critical role for these companies, that generally, these engineers go to the other companies. They work with the network operators or whoever their client is, and then gather the inputs, and they are also involved in the field survey, in order to ensure that a high quality field survey is guaranteed. So Teleworld, Amdocs, these are US based companies worth mentioning, but there are much more around the world. And again, these companies are not just in United States or bigger nations, but it's generally, it can be in anywhere, everywhere, even in South Africa or any other countries. There's always a need for network planning, and generally people are hesitant to spend employees from one country to that country, so they start developing their own smaller companies locally in that particular region where it's required. Just a snapshot of some examples of these companies. So the first tier here on top are the network operators, and the second tier after that white line, you can see they're all equipment manufacturers. Generally, there is a huge crowd on the equipment manufacturers. They have a lot of mass production going on, and there is a lot of openings compared to the network operators, as you see on top. They have very limited positions because they don't do any mass production, but the ones here, they have a lot of mass production and they have a lot of return on their investment. So generally, those are good area to target. But of course, from an architecture perspective, they require the candidates to be really strong. And then finally, a small amount of companies on the network planning site survey services. I believe that's all I have for now.